take the integral of these functions, so I have to assume that the integral exists, and they exist under these two conditions. So then the big question is, supposing that un converges to u, does that imply that the integral of un in u converges to the integral of u in u? This is our question. And I should remind you, note, that when I write un converges to u, and not just me, but most people, then by that we mean a condition that for all x in x, we have un of x converges to u of x. So this is pointwise convergence. Okay, so does this hold? And well, yeah, there are various things there. Good news and bad news, depending on how you look at it. One interesting thing is that supposing that all un are, say, measurable, then we exercise the sigma right here. So this means that they are all measurable. Suppose this holds, and suppose also that un converges to u. So I don't assume anything about u other than it is a limit of measurable functions. Then that implies that u is measurable on these derivatives. This is a result you already saw in chapter 8. So the set of measurable functions is closed under taking point limits. So this is really a very nice piece of information relating to this question. So that if these functions are all measurable, then this is also a relatively nice function. So then, if I call this, let me call this dagger, this whole indication. So one piece of bad news is that a dagger does not hold. I guess it's also, this is where, that is what distinguishes mathematicians from physicists, that a physicist will always, when he or she reads it, assume it holds. And then if somehow it doesn't hold anyway, the physicist will recover it along the way. They very rarely make mistakes, physicists. They do make mistakes from time to time, but they have a pretty good intuition. And mathematicians, on the other hand, they really have to work hard. Every time they see such a thing, they work very hard to prove it exists. And they have some strong theorems that tells you when it exists. And this is what this chapter is about. So the good news, again, so we have some good and bad news, and it does not always hold, but it holds in many cases. And those are the ones that you should hear about here. And one case is actually Devil-Levy's theorem. Which is 9.6 in the book. And that says the following. Suppose we have a sequence of positive measurable functions that says that this function here actually is so the integral makes sense. So what has that got to do with anything? Well, what it has got to do is the following. So let me make a small note. If I have an increasing sequence of real numbers, and if alpha is the beginning of this sequence, then alpha j converges to alpha. I have here to say that I allow for the possibility that alpha could be plus infinity. So I allow for the possibility that a sequence alpha n converges to infinity. So in some cases you will say that, say the sequence alpha n equal n. In this course, that is a convergent sequence and it converges to plus infinity. So in case in other courses you would say the sequence alpha n equal n is divergent, is unbounded. But here it is convergent, it converges to plus infinity. So that is included here. So hence we have in particular we have that if I put u to be uj, uj, then uj converges pointwise to u by this argument. And also I have that the limit as j tends to infinity of integral uj du, that is the same as the soup. So I'm using it to arrive at both of these conclusions, this remark here. So hence, all in all, we have that uj converges to u, and it is positive and monotone. Monotone. That implies that the integral uj du converges to integral. So you can somehow translate Levy into the statement that you have a sequence of functions that converges to u, and converges not an arbitrary one, but it is monotone, the functions are increasing, and they're all positive. In that case, we can make this conclusion. So this is one special case where this question here has an affirmative answer. All functions are positive, and it is monotonely increasing. Okay, and we shall use this fact. The theorems we're going to prove today will use Levy and then also use Fatu-Stella. Those are the two previous theorems. I should make another remark that Levy that is equal to what other books refer to as the Beck's theorem on monotone convergence. We shall very shortly see another monotone convergence theorem, which the book just refers to as monotone convergence with no paper on it. And I'm not a historian. I cannot really justify. It is true that this theorem is referred to either as Levy or as the Beck's theorem on monotone convergence. Both are probably correct and wrong. Physicists really have a tendency of not giving credit correctly. So whoever proved the theorem, I mean, it's, yeah, this I'm not good at keeping track of it. And if you in the literature come across the Beck's theorem on monotone convergence, chances are it is Beck-O'Leary. So this might be possible. Okay, I want to give before commenting one more example, an example that will show that this doesn't always hold. I want to give a statement that you could appreciate in high school. So let me I can even ask a question first. Supposing that we have UN is a sequence of functions, and U is a function, and they are continuous functions from a closed interval, and they take values in the reals. So continuous function from the interval into the reals. And suppose moreover that UN converges pointwise to U. Does that imply so if I know that UN converges pointwise to U, does that imply that usual Riemann interval converges? Can we conclude this? So this is a pure statement about continuous function and the Riemann integral. And as we can see later, this will be the same as the Beck integral. So Riemann and Beck are the same here. So this is really a reformulation of this question, just in a very special case, where we use the Beck measure and continuous function. It's a special case. So what happens in a special case? And the answer in general is no. So the answer is no. Consider, for example, the situation where we take the interval from A to B simply to be interval from 0 to 1. And then let us define some functions that will provide to be a counterexample. Here we have 1. And suppose here I have 1 over n, and here I have 2 over n, and n is a rational number. And up here I have n. Then let me define u and be this function. This should be my function un. So I simply draw the graph. I'm not going to write down the expression. This is the graph of un. And my function u is a function which is identically 0. That's my function u. Then one can check that un converges pointwise to u for all x. So if x is 0, it is all right there. Then un of 0 is over 0, and so is u. And if x is a positive number, then for n large enough, un again is 0 on that one. So that's like this. Okay, so what is integral 0 to 1 un of x dx? Well, it is simply the area here. So that's not, I simply say integral is the same as area. So it's the area of the triangle, and the area of the triangle is 1/2 times the width of the triangle. This is 2 times n, times the height of the triangle, that is n, and this is constant equal to 1. On the other hand, the integral of u of x dx, where u is constant 0, so this is 0. Hence, we see that we do not have to converge here. Okay. So this gives an example also where this fails, and it even fails in that special case. But there is a rescue. And this what I put down now as a theorem will be an exercise for you to do. Not this one, this after. Here. that would be the same situation as before. Suppose given un and un, the continuous function from a to b to be values, such that un converges converges to u. Suppose, moreover, that there exists a number m, a real number, positive, such that for all n and for all x in the input from a to b, we have that absolute value of un of x is smaller equal than number m. So what I'm saying here that all functions un are bounded, well, they are automatically bounded because it's a continuous function of the integral, but they are uniformly bounded. They are bounded by the same constant. All un's are bounded by the same constant. If this holds, then we can conclude that the integral from a to b un of x dx converges to the integral of u of x. And if you look at this example here, then you see that one of the features of this example is as n tends to infinity, the value of un tends to infinity. These are not bounded. There's no m for this sequence of functions. So that's one thing you can notice that this is not a counterexample to that theorem. Another thing that is maybe interesting to know is that, I don't know if you agree with me, but this is really a statement you can principally formulate in high school. If you know about the integral, you can formulate this statement here. But the proof of this statement is if you don't use any techniques, if you just sit down in your knowledge in high school and try to prove this theorem, it's possible to do. You can do it in principle. It's really hard. It's not an easy theorem to prove. However, if you have, and I remember this as a simple exercise, once you have learned the Beck's theorem